I prepared a document about membrane analysis. Analysis of membrane structures. Here, for some easy situations, analysis formulas for some simple membrane structures are given. The formulas are taken from the book's stress analysis manual and theory of plates and shells. The structural analysis of complicated, this is part of my book. You can find using Google, by Googling you can find those books. The structural analysis of complicated membrane structures is generally performed using the formulas given softwares given below. Generally these softwares are used for membrane analysis, because membrane analysis is a complex thing. First of all, in the first step you have to obtain the find the form under applied loads. You have to find first the the form of the membrane under in equilibrium position or very close to the equilibrium position. So geometrical analysis is done here, and in the geometrical analysis, the finite element programs are making iterations to obtain the equilibrium position of the membrane. In the equilibrium position, the internal forces and internal moments and the internal loads composing forces and moments shall be in equilibrium, so that the analysis can be accepted as complete. We have some hand calculation formulas for a circular membrane and for a square membrane, and also the verification examples of these hand calculation formulas by means of Ansys finite element program software is done. The formulas given for circular membrane is valid only if the equation 2-1 satisfies So here this formula shall satisfy so that the vertical deflection and tensile stress formulas are also valid. Now here let's see what the symbols are. Here E is the elasticity modulus of membrane. P is the uniform distributed load on the membrane. D is the diameter of the membrane, and T is the thickness of the membrane. And according to this formula, this amount shall be greater than 250, so that the remaining four formulas are valid, can be used. This here is the vertical deflection of the membrane's midpoint. This point here, you see the plan of the membrane. It's the fixed end membrane, or the edges of the membrane are fixed supported. This is the coordinate r, cylindrical coordinate, and this is the radius r. And the deflected shape of the membrane as a cross section is provided here on the right hand side. You see the membrane's midpoint deflection is obtained by this formula, and any vertical deflection on the membrane here outside the center point can be obtained by means of this formula. And the tensile stress at the membrane's midpoint is obtained by means of this formula, and this here is the tensile stress at membrane's supported edges can be obtained by means of this formula. Here we have a numerical example. It's the verification example given in Ansys. For this example, I used hand calculation formulas and obtained some results. And then in the verification examples, we will see how the verification is performed, and then compare the results obtained from hand calculations and Ansys. So by this way, we will learn to use hand calculation formulas and also Ansys for those types of simple structures which can be calculated by hand formulas. So here, this membrane is given here. X edges are fixed supported. There is a uniform distributed load on it. Its thickness is T. Its radius is 10 inch. Its thickness is 0.0001 inch, and its elasticity modulus is 3 times 10 to the power 7 pound square inch. And Poisson ratio is 0.25. Terminal expansion coefficient is so much, and the uniform distributed load is 0.1 pound square inch. Calculate membrane's midpoints vertical deflection, midpoints tensile stress at and edge points tensile stress using the equations given above. And then repeat all the calculations using Ansys finite element method software. Now you see, we first checked if the hand calculation formulas can be applied here. P is the uniform distributed load, and E is the elasticity modulus, and D is the diameter, and T is the thickness. As you see, the units are compliant with each other here. So the units, the formula should be when the formula is being used by someone, he or she shall take care that the units of the input values shall comply with each other. And it's high enough, greater than 250, so the formula, hand calculation formulas can be employed here. So here, this is the formula, this is the constant, 10 inch is the radius of the circular membrane, 0.1 is, as you know, the uniform distributed load, 10 inch is the radius again, E is the elasticity modulus again, T is the thickness. And we found the midpoint deflection so much. Midpoint tensile stress using the formula is again calculated and obtained as so much, and at the midpoint, and at the support the tensile stress is found so much. The tensile stress is important for us because there is no compression stress for membrane structures since they can't carry the compression stress, only tensile stress. Now, all of them can be calculated using Ansys FEM software. The APDL, Ansys Parametric Design Language algorithm to obtain the results is given below. Write this algorithm in a text file and named as circular membrane dot text. Sorry, I spoke Turkish. Run Ansys in the batch mode and point to circular membrane dot text file as an input file. And run the analysis. It's very simple. Anyone who doesn't know to use Ansys can do this. And to check the results, I will show some basic methods how visually you can see the results. It's very easy. Such commands are easy to use in Ansys. Let's do it. I've done it. Let's repeat it again. From the beginning I will do it. Okay. For the circular membrane, I create a text file. Any name, this is user default name, any name you can use. I use circular membrane. Okay, empty text file. I will copy paste this algorithm into it. I don't know how this mistake happened, but this happens always. Here sorry. No, it should be so. So I pasted the algorithm into the text file, save it to the text file, and close it. Now run the interface of Ansys. You can use as Ansys its interface and run your analysis using the interface. You can use pick commands. You can use your mouse, or instead you can use an algorithm and use a text file to run your analysis. For that reason, you have to select Ansys batch here. Here comes those options. Here as the working directory, you have to show this directory, in which I have saved my circular membrane.x text file, which includes the commands required to run the analysis. Now, working directory would be this. It's on the desktop. This is desktop circular membrane. A job name we have to select. Let's say circular membrane again. It should not be the same as that one. Input file, we have to point the input file as this text file. It's text file, but doesn't matter. You can select that or all files and point circular membrane text file. Alt file name can be remain so, and let's run the analysis. Okay, the analysis has finished. Now check for the errors. There is a warning, but not any error. So, and I see the result file here. So it has completed. We have to change this. This is a backup database file. We have to change the extension of this from RDB to DB to open it in Ansys. So Ansys see this file as a database file. Now let's run the program with its interface. Working directory is same. Now job name, my job is here. Ansys can see it. Now run it. To visualize the results, we see the results from here. We have to let the program read the results because the program, the algorithm has some loading steps. I will explain those load steps soon. We want to see the last results. So I click here. So I have to first click here so that the Ansys software reads my database and results file. My database comes here, and I will now let the program read the result file or the last set in the result file. Okay. Now you see this is my membrane composing of finite elements in two-dimensional. I press on Control in my keyboard and use the right click on my mouse to rotate the membrane. Control plus right click. Okay. To see the deformed shape and vertical deflection, we have to plot results here. For the average values, for the average values, I click here nodal values. For the exact values, more exact values, I shall check element solution. Element solution is non-average, provides me non-average values. Nodal solutions provide me average solution. Okay, degree of freedom solution can be seen only from nodal solution. Vertical deflection. But here, this is the true scale. That's why I cannot recognize the deformed shape. Let's increase the deflections by multiply by a constant instead of 1 true deformed shape. I want to see the 10 times more deformed shape. Okay. This is because the pressure load applied on the areas or on elements because of the orientation or the drawing order or the key points around areas, the surface pressure is applied upwards, but doesn't matter. Now I see it has a ball shape and 0.462 inch is the maximum deflection at the midpoint. What was its calculated value? 0.459. 0.462. Yes, 0.462. Now let's calculate its correctness, or how much the Ansys obtained value deviates from the hand calculated value. Very less. So using Ansys, we obtained almost the same value what we have obtained using the hand calculation. So they verified each other. Now let's see how much is the midpoint tensile stress. Okay, this much. Maximum value is at the midpoint 61,472. Yes. Non-average value, let's check how much is the non-average value. 61,472. Instead of 72, I have 79. Almost same. So average values can be used. But this value is more correct because it's not averaged. But average value can be used. Now let's calculate again how much these two values converge to each other. Again, smaller than 1%. So hand calculation formula and Ansys result verify each other. Now edge point tensile stress. Let's check its value. But we have to select the edge element of the membrane. To do this, first of all, using these commands here, top view, no, front view, okay. I will write here plot to see only the elements, and I will use this command to obtain the edge elements. Element select, new set by means of graphical picking. Click here, OK. Again, apply it. You see only edge elements. Now again, results, but only edge elements are selected. Let's check element solution, X component or Y component. Doesn't matter. Okay. We have the maximum positive values are positive values are tensile. If there is a negative value, it means compressive stress. We will not take care of this because compressive stress, and you see there is no compressive stress. All values are positive. So under the given uniform distributed load, all stresses are positive, tensile stresses. There is no negative stress here. It's 46,742 pound square inch. Okay. Now let's see. This is the element solution, non-average values, and X component or Y component. I get almost the same value. Average value is almost the same. In the X or the Y direction, I will obtain the same result. Now let's again recheck how much these two values deviate from each other. It's, yes, higher than 1%, but 1.7, 1.8% is also very small, very low, and can be accepted. So both formula and the finite element software verifies each other. They with both of them, I obtained the same result. Important note. Nodal solutions obtained by finite element method are indeed average values of finite element results. But now, in addition, we check also the element results, non-average values. However, the nodal solutions given here are checked by the analyst and observed that they are almost same as the finite element results. During membrane analysis performed by Ansys, three loadings are done. First loading is pretension load. This load value is determined by trial and error procedure. If this loading is not done, software cannot make the membrane analysis. Hence, Ansys software is not efficient for membrane analysis. Ansys software is not shown by a suitable membrane analysis software. Those softwares are in industry generally used and accepted as membrane analysis softwares. Second loading is the actual load. Third loading is the removal of the pretension load. Here, when you are using Ansys, it's important by trial and error, and the hard thing is to obtain the value of the first load. Okay. Now I will clear the analysis and restart from beginning, clear and start new. Okay. Everything will be erased. Now let's work on the code. This is the title. Okay. If you, without this, you can also perform the analysis. You can do it by this way. If you copy the codes from the text or write it by your hand here, and then this is the command prompt, and then here press on enter in the keyboard. Okay. Now you see. The title of the analysis is written here. Analysis of a fixed support circular membrane under uniform distributed load. By this command, I wrote this text here beneath the screen. The modeling commands are here. Are here. To enter to the processor, either you will click here or you will copy this code here. Same things. Actually now I did it. Now, finite element type. There are a lot of finite element types in Ansys. In membrane analysis, I use shell 181. And when you write here this one, this means that shell 181 will be the, in my particular analysis, user-defined number is that, my element type. As an element type 1, I will use shell 181. Shell 181 is already defined in Ansys, and I want to use it as type 1 finite element in my analysis with key option 1. And key option 1 means my, actually this is a shell element, but to make it behave as a membrane, I have to make key point equals 1. When I write here 1, then key point equals 1. Is applied. This command is for that one. And then a section type I will define. Section type, first section, this is also user-defined number. First section type is shell section. It's a shell section. And the data related to this first section are given here. This is the command. Okay, this is the thickness of my section 1, and section 1 is belong to my membrane. Its thickness is, sorry, there is a mistake here, 0.0001. If I make a mistake here, it's not important, because after this exclamation mark, I'm writing the explanations. They are not taken into account as commands. Only this part is seen by the program as a command, and when the program sees this mark here, and whatever you write after at the right hand side of this mark, is not taken into consideration by the program. But as a programmer or analyst, later to understand, or for that someone else understand what is given, what is written here as input, you have to write some explanations next to commands. That's why this is an explanation. I made a mistake here, I corrected it. This value is the thickness of the membrane. and section has this thickness and it has material properties, will be given with material type 1. And material type 1, okay, and this is a command. MP means material property, and then EX means elasticity modulus of material, and 1 means the property is provided for material type 1. As you see, elasticity modulus is so much. Thermal expansion coefficient of material 1 is so much. And Poisson ratio of material 1 is so much. Okay, let's enter all those values again. And now I will create key points in the program. 5 key points I will create. We will see them on the program, on the software, on the interface. Okay. Key point 1 is the center point or the midpoint of the membrane. Key point 2, 3, 4, 5 are created with XYZ coordinates. As you see, Z coordinate is always 0. And these lines I need to create. You will see why I create them later. You will understand. Okay, these lines. And I am creating circles. Now the radius is 10 inch. 10 inch. This should be inch. There was a mistake there. 10 inch radius. Now circle. Okay. This is the command circle. Create a circle. Key point 1 is the center point of circle, and then the user provides the radius of the circle. Radius is 1 inch. And it will be constituted from 4 curves. As you see. This distance is 10 inch, but the radius here is 1 inch. Similarly, I create 9 additional circles. All of which has center point at key point 1, but their radius are so much: 2 inch, 3 inch, 4 inch, 5 inch, 6 inch, 7 inch, 10 inch. Copy and paste. You see. Then I use this command. To create a circle. This means create a circle. I forgot. Let's see the definition of this command. You can see the definition of commands from the help of Ansys. For Ansys APDL, command reference. Let's start with C. What was the command? CYL4. Yes. Creates a circular area or cylindrical volume anywhere on the working plane. We will create a circular area. Okay, X center, Y center, and radius. The first options. So X center, Y center, and radius. Radius is 10 millimeter. This is an area. These are lines. 1, 2, 3, 4, 5 key points and lines. Lines, but they are curves. Curves are also lines in Ansys. Curved lines. I have a lot of curves. Lines, curved lines here. But I haven't created any area so far. Now I am creating. And this is a circular area. I created. I have just one area. If you type here area list command, you will see I have just one area. Okay. Again, this command. What is the meaning of this command? Area subtract line. From area 1 subtract all lines. I have just one area. This is area 1. I have a lot of lines. Subtract all lines here in the model from this area. Means that divide this area with all these lines. Okay. I did it. Now, again, I write the area plot and I see instead of one area, a lot of areas. My area 1 is divided by the lines and I have created a lot of areas. Now let's again write the area list command and see I have a lot of areas. And area 1 is not here anymore. Okay. Why did I do to create the finite element solid model by this way? Just to control the mesh of the membrane, I prefer to do it so. Actually, I have divided the area under sub areas so that the program, when the program meshes the areas to produce finite elements and nodes, it makes a smooth mesh. I help the program. This is an auxiliary command. If some nodes are overlapped on each other, the program combines the overlapped nodes. Now I will make mesh. I will mesh the area and create finite elements and nodes. Use type 1. Type 1 element type is shell 181. Use material 1, properties of which I've already given to the program by means of mp command. And use material 1 and type 1. When we are using mesh. Now mesh all areas. And then if some nodes overlapped on each other, combine them and finish and leave the preprocessor. This is the mesh created by the program by its auto mesh algorithm. It's so much smooth as you see here. There are some triangles created here. This is what Ansys do. Now let's enter to the solution commands. Start the solution phase. Either you click here or you write this command on the command line. Analysis will be static analysis. It will be geometric analysis, force controlled, convergence or the results are controlled by the forces and keep only the last results You know, program is making in the nonlinear geometry analysis some iterations, sub-steps and under sub-steps iterations. I want the program keeps in its memory only the last results the program calculates. Okay, load. This is temperature, uniform temperature load. It's minus 50 Fahrenheit. This is a verification example taken from Ansys. Someone, by means of trial and error, determined this value. The important thing in membrane analysis is to find the pretension load. Someone has done it. Why it is minus? Because it provides contraction of the membrane. So it creates tensile stresses in the membrane. The load is given. Now, cylindrical coordinate system will be selected. And when cylindrical coordinate system is selected, since this is a circular membrane, location of nodes at the edges are selected by means of the second command. Node select a new set location in radius direction. X means for cylindrical coordinates in the radius coordinate. Radius is 10. So only the nodes at the edge of the membrane will be selected. And then make all of them fixed support. This means that you see fixed supports are placed at the edge of the membrane. So here, by means of this command, the midpoint is selected. Midpoint not selected. So there is just one node. Then and the deformed shape will be symmetric about the midpoint, about the axis which is perpendicular the results, the deformed shape will be symmetrical about z-axis, vertical axis. These commands provides that, and number of sub-steps will be 20 for uniform temperature load minus 50 Fahrenheit degree, and make the solution. Meaning of the commands. This means make step loading. Sorry, not ramp loading, but step loading. Instead, in Ansys, for example, if you have one load value here, one load value here, one load value here, don't do that. The loading is not so. The loading is so applied. So. Now surface pressure 0.1 pound square inch. Number of substeps 20. Solve again. Now this is the real load. Solution is done. Now removal of the pretension load, which is given in the beginning, and the most important thing in the membrane analysis when you are doing quick bindings or Ansys, using Ansys. Remove it. Okay. Solution is done. Again, read results. Results summary. We have 3 load steps. Okay. Program applied 7 substeps in each load step. In the first load step, program made 8 iterations. We need 7 substeps. As I understood, 7 substeps. Each substep has 1 iteration, but one substep has 2 iterations. So cumulative 8 iterations, 1 more. Here the number of cumulative iteration is 22. 22 minus 8 makes 14. So 14 iterations are done here under 7 substeps. So per 1 substep 2 iterations are done, and in total 29 iterations are done. Okay. 21 substep and 29 iterations are done to obtain the solution. Now read the last set. Last iteration, the results of last iteration we want after removal of the pretension load. We want to plot the results, nodal solutions, degree of freedom solution, vertical deflection. Now you see again same result. Let's do it with user specified or increased deflections. You see. Again the same value. Let's check the value of stress. 61,482. Midpoint tensile stress. So this is nodal solution. They should be equal, but a little difference after decimal. Appears here. These two maximum values at the center, they should be equal. 61,482. How much is that one? A similar value. How much is that one? A similar value. This is a software program. I should have obtained the exact the same value here. But we see here the software program. The better is writing all documents in a text file and let the program read it as a single file and perform all the load steps without making any break. But here the analysis can also be done by copy-paste method, and in detail I try to explain the meaning of the commands here. We can also check if the X stress value change. Element select, new select, using graphical picking. I think 1/4 is enough. $46,750. A bit, it has changed also a bit. This is the average value. This is nodal solution. Average value, yeah, it has changed. Element solution, did it change? Doesn't matter, X or Y. Yes, 46,749. I don't know why the values has changed. It's related to the program. But I think writing it in a text file and let the program read it completely as a continuous and pursues the command in a continuous manner is a better solution. So the values given here are the correct values. So I have shown the solution of a circular membrane by means of head calculations and let's say Ansys. And then we will see the calculation of square membrane and finish this video here. Please subscribe to my channel. I will put this document here. This is my website. Later, somewhere you can read it in English.